Hi, this is Sholey Physics episode on Freefall lab data collection. Hopefully you've just collected your own data using Vernier video physics or some other method, or you may have been looking at my example of the videos I took of the drops, and you may be using my data. This particular set of data that I'm using today is from the 200-gram mass that was placed in the empty box. So it's no longer empty, and it was dropped. And before I move ahead, I just want to say today is brought to you by Inigo Montoya. You killed my father. Prepare to die. Well, I'm not threatening you per se. It's from the awesome movie Princess Bride, arguably one of the best movies of all time. If you've never heard of it, you need to see it. Inigo Montoya, he's one of my favorite characters. Anyhow, back to the lab. Here's a video. I'm going to play the video of this particular dropping the box. And you'll see those data points that were recorded, or in the red dots. And what happens as it falls is those data points are becoming more and more separated. That means for every time interval, the box is falling at a faster speed and moving a greater distance. So that's separation. We're going to see that separation in just a moment. It's going to get larger and larger and larger as it falls. Going to the graph, you can see this close to the beginning of the drop. You'll see the box is at a position of about 1.95 meters at about 0.02 seconds after the starting clock. And the next point, so that is 0.02 seconds, 1.95. The next point is at 0.04 seconds, so a small time interval later, it's still at 1.95. So I must not have dropped it yet. Okay, we'll track this one again. 0.04 is 1.95. This next, there we go, we get a little bit of change there. The next segment, 1.94 meters, we're at 100th of a second later. So for a 100th of a second interval, it's dropped 1/100th of a meter. Later on, let me check a couple points down here. At 0.52 seconds, it's at 0.69 meters. And just a moment later, 0.54 seconds, it's at 0.6 meters. So you see that there's a bigger difference of 0.09 meters for that very, very small time interval of change. So as this box is falling, it's falling faster, so that makes it cover a larger distance in the same time interval, and that's why our dots are getting farther and farther apart. Now let's look down here at what's happening at the bottom. This is a velocity time graph. First off, what you might note is all these values are below zero. This is a negative acceleration that's happening here, so it's getting faster in the negative direction. At 0.05 seconds, the speed was 0.59 meters per second. And later on, 0.4 seconds after the starting clock, it's moving at about 3.88 meters per second. So it's gotten faster as it's falling, but it is getting more falling in the negative direction. All right, so how do we calculate acceleration from this data? First, we're going to go to the definition of acceleration. Acceleration is a change in velocity over a change in time, or a rate of change in velocity. And a change, this delta, means the final condition minus the initial. And also we have the same thing on the bottom. We'll take the final time minus the initial time. Now if you watch one of my other episodes when I introduced this as an equation, I just said, oh, the starting time is usually 0, so let's just call it the amount of time it took for the speed up or slow down for the acceleration period. But in this case, we do have 2 points where the first point is not necessarily at the 0 time mark. So what we're going to run into over here in the graph, as you'll see, at the very beginning of the data collection, this data doesn't look quite right. The box didn't go up, or didn't decrease in speed and then increase again. It was just dropped. So perhaps I collected some strange points of data up here. You might remember how these 2 points are at the same exact height level. So in the beginning, my data is a little off. But what I can count on is as I look at the trend of this data and the velocities, they're all in a straight line. So they're all agreeing with one another. All these points look like pretty good points. I also run into some problems here at the end. the velocities don't look quite right. They're not following that same trend. And what happens is in the video, when everything gets all blurred, that's interesting. In the video, when everything gets all blurred, it's hard to pick these points out. So I probably picked the wrong points, but the rest of this data from that's all in a line. This is something we can count on. So what we want to do is pick out an initial velocity point and some kind of final velocity point along that dependable line of data that shows a good strong trend. So I'm going to start up here where it looks like this trend is beginning at 0.05 seconds and 0.59 meters per second. And I'm going to pick the last one that looks like it's in line. This is at a speed of 4.03 meters per second. So just for argument's sake, yes, I know it's in the negative direction, it's falling down. So I'm just going to get, not really focus on the negative aspect of this. The velocity going downwards is 4.03. So where do I plug this in? Oh, by the way, if you look at the form of this, doesn't it look sort of like a slope? If you calculate the slope of a line and you have 2 points of data on that line, you can take the rise divided by the run, which is y2 minus y1 divided by x2 minus x1. And sure enough, we have velocity on the y-axis and time on the x-axis. So that's exactly what we're doing here. I'm going to take the final velocity, 4.03, and we'll subtract the initial velocity in just a moment. And the final time, so 4.03 was the speed, right over here. So we're focusing on this part. That's the speed. And the time at that moment is 0.42 seconds. Okay, so we're going to plug in 0.42 for that final time. All right, moving on to the first point. I'm going to pick that one up here. 0.59 meters per second is the initial velocity at 0.05 seconds. All right, so I'm going to find that difference there. This looks like 31 plus 0.03, so 0.34. This is about 3.34 is that difference, divided by 0.37 seconds. Now all I need to do is calculate that difference. I'm going to grab my calculator. 3.34 divided by 0.37. I get 9.027. I'm going to just round it to 9.03 meters per second squared. That's the acceleration unit, meters per second squared. And where did I get that from? Well, this is a difference in velocity, which is in meters per second. I'm dividing it by seconds again. So that's how you determine the acceleration from your graph. Just to recap, find the section of your velocity data that agrees that's showing a trend. So there's a nice straight line from the top here down to about right there. Pick a point near the bottom, that's your final. Pick a point near the top, that's your initial. Plug in those two final and initial velocities and the final initial times. Take the difference and calculate your acceleration that way. I hope this is useful in finding accelerations for your free fall data. Thanks for watching.